All right, so I'm going to talk a bit about Nvidia and OpenMP. We've been involved with OpenMP for a long time, and one of the complaints that we've gotten is Nvidia/PGI doesn't have an OpenMP 5.0 compiler. Well, we don't really have one yet, but we just talk about the precursors of it. All right, thanks. I'll eat it if I have to. Just keep reminding me. See if these slides will progress. That's interesting. My slides are moving. Let's just do this. There we go. All right, so I'm going to go a very brief bit about what OpenMP is, mainly because I'm going to give comments about what it is, not the specification itself. Then I'll talk about NVOMP, which is the OpenMP implementation we have that is CPU and GPU aware. And then talk a bit about future work, and depending on how long it takes, I may talk more down here than up here. So what is OpenMP? So these are the constructs that really matter to us, in my opinion. There's a parallel construct, which just starts multiple threads. There's all of the loop constructs that cause you to be able to cause those threads to work together. Then there's the task construct, which is kind of this precursor to lambdas and closures and all this stuff as far as OpenMP is concerned. So OpenMP has had tasks for a while. It's just, if you think of it as a lambda that gets deferred, that's all it is. Target, which is a horrible compromise. Teams, which starts up multiple teams of threads, which are a league within a target construct. So it's now can be pulled out and executed outside of a target construct, so that you end up with this thing that has limited communication between itself on the CPU. And many of the CPUs, and Intel actually is the one who pushed to get this onto the CPU. The CPUs are getting big enough that they're NUMA within themselves, so you don't want to communicate if you don't have to. So this tells us you're not going to communicate. And then the distribute is the way that teams work together. So you can actually take these, put them up here, and all of a sudden this starts shrinking down. And at the end of the talk, I'll talk about that a little bit. So this is a slide. If you were here earlier this morning, Uri put this slide up of what OpenMP5 looks like. There's a bunch of stuff up there. It's a cool slide, so I put it up there. The more interesting slide is this one. And so this is where we're at today. The blue is the interesting part because that's the CPU side of things that we have fully implemented or reasonably fully implemented. The green is the GPU offload side. As Uri said this morning, it's not been released completely, so we're talking about it. You can go see them talk about it in the Nvidia booth, but it's not something you can download and use right now. So this new Nvidia OpenMP runtime is actually based on the LLVM runtime. We picked it up and tore all the guts out of it, kept the interfaces, and re-implemented everything. We did this so that we could extend it to understand both the CPU and the GPU. So we actually can reuse a lot of the code both on the CPU and the GPU and have them understand what's going on in a reasonable manner. We do have some GPU unique interfaces right now. They're mainly unique because nobody else we haven't figured out how Clang's going to do it. So maybe we'll standardize later. Right now they're different. The big thing here, and Uri talked about it earlier, we use the same present table that OpenACC uses. So you have automatic interaction between OpenACC parts of your code and OpenMP parts of your code. This runtime started out as a 3.1 implementation. We had no aspirations actually of going beyond 3.1 originally because that was the code base that we started with, saying this is what we need to get running onto the GPU. Then PGI said we need a new runtime for our LLVM compiler, and you have something that works reasonably well and understands GPUs, so all of a sudden we became a 5.0 compiler, runtime and compiler. Big limitation, we have tasks implemented, but they're really 3.1 tasks. Anything that's beyond 3.1, we really haven't implemented yet. It's just not there. And one of the dependencies is just nothing. We don't even know how to implement it in our stuff yet. So our goal, and there's a reason there's no numbers there because I don't care about the numbers. Our goal was to have these lines basically be the same. So the blue side is what ships with playing right now with LLVM, and the reddish orange, whatever, it looks more orange on my display here, is the performance of the NVOMP. So as you can see, it's fairly flat. This is missing because of a bug in the compiler. This is faster because one of our developers spent a week staring at the code and find one minor change and he could make it faster in our system. So this is the part that I'm most interested in. The next slide. So we don't have any of the SIMD stuff done. If you talk to the Cray people, which I was one of the Cray people that did this decision back then, they ignored the SIMD. It was actually just a bit we set in the loop structure saying that try to SIMDize this thing, try and vectorize it. PGI is taking a similar approach. They're going to try and auto-vectorize. We'll come back to SIMD when they have time. OMPT, OMPD, that's a huge part of the specification, and it's not a priority. That's why it's not there. It's not that we don't think that it's useful. It's just, it's a lot of work, and we have to pick our battles. DepObj, again, we haven't done anything with dependencies yet, so why would we have DepObj? Scan, again, it's just, we're not there. We have to get that far. Allocate, there's a lot of discussion around allocate on whether or not we will ever implement it. It's a really complex beast, and until we see use cases that actually benefit from it, and there's things in the wild that say we have to implement it, we're going to probably keep back from it. Declare reduction is again, it's just time. It's a big thing to do again. It's a lot of infrastructure to add, and we just have to have the time to do it. And it's a lot of infrastructure both in the compiler and in the runtime. Declare mapper, again, infrastructure, time. Combine target constructs. This is an interesting one because you'd think if you have one part of it, you'd have all the parts of it. But if you had come to Gurai's talk, PGI is picking and choosing what they want to implement so that you get as close to OpenACC performance with your OpenMP as you can. So they want our users to be able to look at the code and say, okay, we're getting good performance. We don't want them coming back and complaining they're getting bad performance because they wrote bad OpenMP. So that's the reason right now. In the future, we'll have to keep up with whatever Clang does. It's a fact of life. So, but we have to do something, and this is where we're at. And then the meta directives. This is something we don't even know how to implement yet. In the next slide I'll talk about meta directives a little bit more, but we're trying to figure that one out because we need it. We know we need it. It's a really important feature that makes OpenMP useful for the CPU and the GPU. And if we don't have it for both, then a lot of if you know the PGI compiler, it's been known for its ability to generate code that works on multiple different CPUs and different GPU type things. So, right now we're only Nvidia GPUs because AMD went away and all these other things went away as far as PGI was concerned. But our users need to be able to say, okay, I want this to run optimally on the CPU or I want it to run optimally on the GPU and not have overheads in place from one or the other. All right, so this is the part that I wanted to talk about the most. So right now we're looking at 5.1, so we're going to be a 5.0 compiler. 5.1's in the future. We're still trying to figure out what 5.1 matters, what we need to implement. And Jeff and I have to figure out between us so we can actually try and convince PGI what it is as well. One of the things, we've actively used this new runtime to do some experiments. We've actually done things that other members of the language committee have proposed, and we've played around with them to see how they work, what were the overheads, and what could we do? So how could we actually exploit things on the GPU? How can we do things on the CPU? And we've actually got some numbers back that we found were much better than what people were saying. They were much overly pessimistic on the expectations, so we're happy with that. We have a task loop implementation. Our task loop implementation is quite possibly the most brain-dead implementation you can ever put in a runtime, but we don't have a compiler to tie to it, and we don't have any benchmarks to tie to that compiler, so we have no idea what we need to do there. Do we even care? So until the compiler team gets a benchmark and the benchmark actually needs performance, we're going to have a bad implementation. But we do have an implementation, which took very little time to do. I mentioned earlier the meta directives. The meta directives that are in 5.0 are flatly broken, and you can't actually do with them what we need to be able to do. At compile time, you're supposed to be able to choose, am I running where, and optimize your code. Are you running on the CPU or running on the GPU? It turns out the way we actually wrote it in the specification is either misinterpreted by one part of the language committee or the other. Whichever part is wrong doesn't matter. What matters is users can't write code that's portable. And that's what we do. So we need to fix that in 5.1. So we will be working very hard to get that fixed. PGI discovered the problem. Nvidia is driving forward as hard as we can. And everybody else has jumped on it. And we'll have a solution. It's just a matter of, this is really, really important to us. So the two feature things that are interesting to me that are future looking for 6.0 type timeline. Do we really need target, teams, parallel, and task? We have all of these different ways of starting parallelism. And if you look at target, target actually explicitly says it's a task. It's just a special kind of task that runs work or someplace else. So the task could have been what we used. Teams is really parallel, but we didn't want to put a clause on parallel because if we put a clause on parallel, parallel goes from being able to synchronize to not being able to synchronize. But do we really need either of these actually? Because if we take these and think about them as just a unit of work that needs to be done and say, okay, a task is a unit of work that could have multiple threads execute it, we can fold all three of these into task. We have a single execution engine, the task, that gets scheduled someplace and is run by some number of threads. And this is something that we've talked about for about a year, and we keep pushing it off because it's not something we can do without a major change to the specification. So we'll start pushing on this for 6.0 to see what happens. And then the other really interesting thing is if you look at all of the tasking tutorials, they tell you to do parallel master and then a for loop around a task. And that's how you get tasks spawned and execute them. Why do we need the parallel master? The only reason we need the parallel master is because tasks need to have threads available to them to be scheduled on. And parallel is the only way right now in OpenMP to get those threads available. And we've shown to ourselves that this is a bad idea, and there are relatively low overhead ways to fix that problem. So that's another thing that the language committee has been looking at off and on, and hopefully in 6.0 we can